Welcome to the Fun Infrared Learning Series. This episode, Ep14, Introduction to Sampling Techniques. A. Attenuated total reflectance, the most common modern. Then close with a checklist. Next, a peeping invention. In 1959, physical chemist Johannes Fahrenfort at the Royal Dutch Shell Laboratory discovered a peculiar phenomenon while studying interfacial phenomena when light travels from a high-refractive-index medium to a low-refractive-index medium, and the incident angle exceeds a certain critical angle. Total internal reflection occurs, but the reflection is not perfectly clean. A portion of the energy smuggles into the low-refractive-index medium as an evanescent wave, where it is absorbed by molecules. Fahrenfort keenly realized, isn't this an excellent infrared sampling method? Simply place the sample on the crystal surface, allow the infrared light to undergo total internal reflection within the crystal, and the evanescent wave will peep at the molecular information of the sample. No sample preparation, no pellet pressing, no liquid sound needed. Next, physical principles of ATR 1.1 reflection, and total internal reflection. To understand ATR, let us first review the phenomena of diffraction and reflection of light. Next, ATR crystal materials. 2.1 Why are high refractive index crystals needed? From the critical angle formula that tag equals sin 1 2 none dollar, it can be seen the larger none crystal refractive index. The smaller the critical angle, the easier to satisfy total internal reflection conditions. Most organic compounds have and $2 approximately equal 1.4-1.6. Therefore, H crystals require none greater than or equal to 2.0 to operate reliably. Next, single bounce vs multi-bounce ATR structure. Infrared light undergoes only one total internal reflection inside the crystal before exiting to the detector. Characteristics: side weaker signal, only one reflection. Absorption: small sample volume, small reflection point area, approximately 1-2 square millimeters. Next, sample contact and pressure mechanism. 4.1 Why is contact so critical? The evanescent wave in ATR penetrates only 0.55 micrometers into the sample's surface. Therefore, close contact between the sample and the crystal is key to successful ultra. Next, the advantages and limitations of ATR applications. 5.1 Core advantages of ATR. Bruker summarizes 5 main reasons why ATR has become the mainstream technique. Next, ATR spectrum is transmission spectrum. 6.1 Origin of morphological differences. Although ATR and transmission spectra have similar peak positions, there are systematic differences in peak intensity distribution. Next, modern ATR instrument integration. 7.1 Major manufacturers 8L products. Bruker outcome platinum ATR diamond single reflection. Pneumatic pressure integrated in Alpha E and Sin series. Lumos fully automated micro trait for small samples HTSXT. High throughput ATR with 96 well plate. Next, comprehensive comparison of ATR and transmission methods. 8.1 Comprehensive comparison table. Table 6 Comprehensive comparison of ATR's transmission. Next, their applications of ATR. 9.1 In situ reaction monitoring. ATR can be used for in situ monitoring of chemical reactions, dropping the reaction solution onto the ATR crystal real-time. Spectral acquisition, 1 spectrum every 30 seconds. Monitoring reactant consumption and product formation. Applications: polymerization, esterification, drug degradation. Next, historical review and future outlook. 10.1 Brief history of ATR development. Table 7 Brief history of ATR development. Next, review questions. Using a diamond ATR, none equals 2.4. Incident angle 45 degrees at green to measure a polystyrene sample, and $2 equals 1.59. Calculate the critical angle and the penetration depth at 1000 centimeters. Hint: lambda dollar equals 10 micrometers. The same sample is measured by a transmission. Finally, the drill actualists. Make sure you can recall each item. Core knowledge points. Key points. AA principle. Total internal reflection of light in high refractive index. Crystal evanescent wave penetrates sample surface 0.55 ohmmeters. Critical angle formula. $attack equals send 1 to none. Requires $none and $2. Penetration depth. $dp equals 1a 2p none. Sunset truth 1002 none ek $2. Penetration depth characteristics. Proportional to wavelength. Low wave number peaks relatively stronger. Diamond entree. Modern standard. Highest hardness. Chemical inertness. Wide spectral range. Safe. Dense artery. Economical choice. Refractive index similar to diamond. Good soft. Not resistant to acids. Bases. Surface analysis specialist. Highest refractive index. 4.0. Shallowest penetration. Fahrenfort application. High hardness. Moderate refractive index. Single vs multiple reflection. Single mainstream diamond standard. Multiple liquids. Trace analysis. Sample contact. Good contact is key. Requires pressure mechanism. Spring. Pneumatic. AS transmission differences. Low wave number enhancement. Peak shifts. Require tree correction. Enter advantages. No sample preparation. Non-destructive, fast, wide applicability. After limitation. Surface selectivity not suitable for gases. Spectra need correction. Historical milestones. 1959 Fahrenfort discovery. 1990s diamond, atoll popularization. That covers the required sample for this episode. Practice with real spectra on Fun and continue with the next lesson.